How can you locally approximate a multivariable function nearby a given point? Multivariable Taylor's theorem provides a brilliant solution using multivariable polynomials. You can approximate many functions with a polynomial of degree 0, 1, 2, 3, or higher. This theorem is a profound achievement of multivariable calculus. The formal statement is a bit complicated, but the visual provided here illustrates the key ideas. In this video, you will learn how to interpret the formal statement of multivariable Taylor's theorem using the displayed animation. This process will provide insights from algebraic, analytic, and geometric perspectives. Let's start by reviewing the definition of a Taylor polynomial. There are many valid definitions. Here is one. Fix a positive integer n. Let f be a real valued function, that is Cn on an open ball at a point A in n-dimensional space. In other words, all the partial derivatives of f up to order n exist and are continuous on this open ball. The nth Taylor polynomial of f at A is the n-variable polynomial, denoted p subscript n, defined for all x in Rn by the following formula. As you can see, this expression carries a lot of dense notation and information, so let's unpack it. Here, alpha is a multi-index with n indices of natural numbers, so each component is a non-negative integer. Alpha factorial is the product of factorials of the components. The degree of alpha is the sum of its components. The alpha partial derivative of f is defined as the following combination of partial derivatives of f. The first variable is differentiated alpha 1 times, the second variable is differentiated alpha 2 times, and so on. The expression x minus a to the alpha is the following product of monomials. Before continuing with this video, I encourage you to read an introduction to these formal definitions along with some computational examples. That said, let's next review an example to just make everything concrete. Our example will concern a two-variable function. Let f of x1, x2 be the function x2 minus 2 times e to the negative x1 squared. So this function f is C infinity everywhere. In other words, all of its higher order partials exist and are continuous. Fix the point a1, a2 to be the origin in R2. For a positive integer n, the definition of the nth Taylor polynomial can be rewritten in the following special form for the two-dimensional case. Take a moment to check that these expressions match the original general version. Now, using the formula, you can compute the first few Taylor polynomials. The zeroth Taylor polynomial is negative 2. It is a degree 0 polynomial. In other words, it's constant. The first Taylor polynomial is computed with all the partials up to order 1 and is equal to negative 2 plus x2. It is a degree 1 polynomial. In other words, it's linear. The second Taylor polynomial is computed with all the partials up to order 2 and is equal to negative 2 plus x2 plus 2 times x1 squared. If you'd like to check these calculations or read additional computational examples, now is a good time to pause the video and do so. Remember, our goal is to interpret multivariable Taylor's theorem through a visual animation. We will continue with this two-variable example in mind. The graph of our two-variable function is plotted here in three-dimensional space. We want to approximate the function f at a point x near a. Note x and a are two-dimensional quantities. The 2D value a corresponds to the 3D point a, f of a on the graph. We call this the center of our approximation. The 2D value x corresponds to the 3D point x comma f of x on the graph. Taylor's theorem explains how to use polynomials to approximate the value of f of x as x gets closer to a. We are now ready to describe the formal statement. Fix a positive integer n. Let f be a real valued function that has continuous partials up to order n on an open ball at a. Taylor's theorem has two parts. Let me state the first part. If Pn is the nth Taylor polynomial of f at a, then the following limit is equal to 0. We often equivalently say that Pn is an nth order approximation to f at a. Let's break down this limit expression a bit more carefully. The quantity in the numerator, f of x minus Pn of x, corresponds to the error between our function and the Taylor polynomial at the point x. The quantity in the denominator, namely the norm of x minus a to the n, gives a benchmark for the rate of the error's decay. If x is very close to a, meaning the norm of x minus a is close to 0, then this denominator is very small. Indeed, a larger value of n will correspond to a smaller denominator. By taking the ratio of these quantities, we are comparing how fast the error tends to 0 compared to the norm of x minus a to the n as x approaches a. Taylor's theorem says that this ratio tends to 0, meaning that the error tends to 0 faster than our benchmark denominator. For example, if n is 100, this error with the nth Taylor polynomial as x approaches a tends to 0 really, really fast. Now, how can we visualize this formal mathematical statement? Returning to our example, let's look at a few different Taylor polynomials, starting with n is 0. We can plot the graph of the 0th Taylor polynomial of our function. Since the polynomial is degree at most 0, this corresponds to a constant. So its graph is a flat plane. Taylor's theorem compares f and Pn at the 2D value x near the 2D value a. So we are comparing the 3D point x comma f of x with the 3D point x comma Pn of x. Notice these points must lie directly below and above each other. The error in Taylor's theorem, namely f of x minus Pn of x, is therefore equal to the difference in the heights of these points, illustrated by the length of this yellow line segment. Taylor's theorem says that this error tends to 0 faster than the norm of x minus a to the n. For n is 0, the denominator is a constant, so the statement simply means that the error tends to 0 and nothing else. That's not really so surprising, since it is equivalent to the statement that f is continuous at a. What about the case n equals 1? The first Taylor polynomial is linear, and therefore its graph corresponds to a tilted plane. The denominator in Taylor's theorem is equal to the norm of x minus a. In other words, the distance between x and a. The theorem therefore states that the error tends to 0 faster than the distance between x and a, and in particular, faster than before with n is 0. Watching the animation, you can see that the error shrinks faster. However, this statement is again also not that surprising, since it is equivalent to the statement that f is differentiable at a. The really interesting stuff happens when we look at values for n at least 2. When n is 2, the second Taylor polynomial corresponds to a quadratic polynomial, and the denominator is now the square of the norm. Therefore, the error tends to 0 even faster than the square of the norm. And when n is 3, the polynomial is cubic, and the error tends to 0 faster, and the same pattern continues for higher and higher degrees. Starting from n is 0, the error goes to 0 faster and faster and faster. This animation captures the first part of Taylor's theorem. Before moving on to the second part, I want to highlight a common confusion when interpreting these pictures. There are two key variables, n and x. One is fixed and one is varying. We must be careful about which one we are fixing when interpreting the picture. If the positive integer n is fixed, we're looking at one surface. In this case, Taylor's theorem does imply that Pn of x approaches f of x as x approaches a. It also tells us it does this faster than x minus a to the n goes to 0. If the 2D value of x is fixed, then Taylor's theorem does not imply that Pn of x approaches f of x as n goes to infinity. The pictures really seem to suggest that that is what's happening, but that's not exactly what Taylor's theorem says. This is an exciting new question, and it's actually about multivariable Taylor series. This involves adding up infinitely many terms in a polynomial. That's a completely different and equally exciting story, but we won't venture into it here. Let's return to Taylor's theorem in the second part. Recall that the first part says that the nth Taylor polynomial is an nth order approximation to f at a. The second part says that the nth Taylor polynomial is the unique polynomial of degree at most n satisfying this property. This feature makes Taylor polynomials extra special. Notice that the condition that the degree is at most n is crucial. There are infinitely many polynomials of degree n plus 1 and higher that will satisfy this property. The Taylor polynomial is therefore the polynomial of smallest degree, which is an nth order approximation. Informally speaking, you can think that this has the least possible complexity while maximizing the quality of the approximation. Let's visually interpret this uniqueness property. Consider the n equals 1 case, where the first Taylor polynomial has degree at most 1, and hence its graph is a tilted plane. Any other polynomial of degree at most 1 will also have the graph of a tilted plane. Now, the Taylor polynomial approximates f with some error. That is the distance between this green point and the blue point. The arbitrary polynomial also approximates f with some error. That is the distance between the blue point and the red point. So it's a much longer distance here. The second part of Taylor's theorem says that the error with Pn will always go to 0 faster than the error with P. You can see that this is happening in the animation. Now, you might say that I chose a polynomial P which had no chance of beating Taylor's theorem since it already had a bad head start. So let's actually give it a better chance. So I'm going to rig things to make this polynomial be a little bit closer to our graph of f than the Taylor polynomial. Let's see what happens here. Who's going to win? Let's zoom in right there. That was a critical moment. And I'm going to rewind. So blue to red is very small here. It looks like red's winning the race to blue. But you'll notice before it gets to the point A, blue actually starts coming closer to green right here. There's a switch. And the distance between blue and green is actually shrinking faster and faster and faster, and it gets closer to green before it reaches the point A. This is what it means for the second part of Taylor's theorem, that no matter which polynomial you choose, you're always going to see the error with the Taylor polynomial shrink faster as it approaches A. This pattern continues for n is 2. Any other polynomial p of degree at most 2 will approximate f with some error. But the error with p2 and f will always go to 0 faster than the error with p. The same is true for n is 3. And n is 4. Overall, Taylor's theorem is a remarkable achievement. At any given point, you can approximate any smooth multivariable function by a multivariable polynomial of any degree. As the degree grows, the error decays at a faster and faster rate. For any given rate, the Taylor polynomial is the unique polynomial of smallest degree with this fantastic property. They really should be called tailored polynomials because they were tailor-made to fit any function.